Okay. Thank you all for being here today. My name is Omar Hashash. I am a postdoc at Virginia Tech. Um, Today, I'll be presenting one of our recent works, which frames active inference as a test time scaling law for physical AI agents. So these two terms have been rhyming a lot in AI literature over the last couple of months. And I should also here notify that my colleague, Christo Thomas, who is an assistant professor, he could not make it today due to the rescheduling. But I do have to thank the TMB chairs for uh, managing to put down a new ad hoc meeting this week as fast as possible. So thank you for that. Thank you for managing this. So without any further notice, okay. So this is just a glimpse about me. As I said, my name is Omar Hashash. I'm a postdoc now at Virginia Tech, USA. I earned my PhD recently, back in December 2025, under the supervision of Professor Walid Saad in the Electrical and Computer Engineering Department. I finished my undergraduate and master's studies back home in Lebanon. I did my PhD around wireless communications. So basically, what we know now today as 5G and the next generation that's coming after that, which is known as to be 6G, and its intersection with AI, and especially we focused on two main technologies, which are digital twins and world models. And from there, things intersected with a lot with active inference and neuroscience itself. So my work had a lot of discoveries along that path. Today we're going to be discussing a lot of them. And this is just a glimpse of my colleague Christo, who is now an assistant professor at WPI in Boston, USA. During that time when I was working on this work, he was a postdoc still at Virginia Tech. So we worked on this work back in 2024 to 2025, after him joining WPI after that. So to start first, I'm gonna first probably put down a roadmap about this presentation. So it's roughly gonna be divided into two parts. The first part, which basically covers around one third of the presentation, around 10 slides, which is the basic motivation of how someone that's coming from a wireless communications background and would end up in a theoretical neurobiology group presenting today. And of course, along that route, we're going to intersect with AI and show how we can jump from AI to neuroscience again and do the whole connection altogether. So uh, I think everyone now kind of acknowledges the fact that AI is the most transformational technology that everyone is anticipating in all the different fields today, and wireless networks are just one of those fields. So 6G networks, the next generation of networks that we have today. So what we have today is basically 5G networks, the fifth generation of wireless networks. And with the advent of 6G networks, we're going to more encompass AI more into our network. So think of these as your base stations that you see along the road while you're driving next to your home, the signal, the where you get your communication signal to call to get your phone. Um, so we started actually implementing AI in our networks back in the days, and we already started touching on improvements in what we call today as AI native networks. So AI is built natively in the network itself, and we've recorded a lot of astonishing progress over there. We started seeing improvement in terms of energy efficiency, in terms of the latency, in terms of the capabilities that the network can now deliver, especially that you have this intelligent entity that lives inside the network itself. But that's only the good part of the story. Just like with any technological revolution, you always have the good, the bad, and the ugly. Now, what I said now was just the good part of the story. What remains is the bad and the ugly. And this is how somehow how they look like. So till now, what we have in terms of these wireless communication networks is that we train these systems over lots and lots of data, and these systems fail as we plug them into the real world. So, for example, we have here, this is what we call as a 6G air interface, where basically we have kind of a communication signal that needs to be sent from a base station to an agent, for example, or to a human, or to you, for example, or to me. And that decision is based on lots and lots of data. So what happens in the world is that the world faces a lot of distribution shifts, which is a very known problem in AI. And with those distribution shifts, the efficiency of that process falls down. It collapses. Rather than just the communication part of the story, our networks are also gonna connect these physical agents in the world. So these physical AI agents I was talking about in my title. So not just connecting you and me, just like now what happens in 5G networks. In 6G networks, we're gonna connect these autonomous physical AI agents that are in the world. But we can see now also that these agents, although we have a lot of training data for them and we've trained them on probably millions and millions of driving trials, they still fail in the world, just like this vehicle that you see over here. It falls off a cliff, for example. And this also carries out the same thing if we were to talk about robots. So, for example, this is here a robot that's been trained to win Olympics, but still crashes on the track with a pedestrian that is just crossing over there as if it's blind. And ironically, we now have an AI system that can win the math Olympiad, but fails at this type of Olympiad. So we can possibly pose down a question around here and say like, why is this today's AI is good enough to win a math Olympiad, but it fails in this type of Olympiad, or basically more general, it fails in very simple real world scenarios that any human can excel in. So I'm not going to answer this now, but I'm going to use it as a motivation for the rest of the presentation to say that, well, probably we're missing something big and we need to figure this out. So to start first to know what is the big thing that we're actually missing, we should start first to ask the question and say, what are we actually, what do we want this AI to do? What we want this AI to do is we want it to be adaptive. We want it to be generalizable. We want it to learn just from a limited amount of data and generalize that experience into the world, just like we humans do. We want it to adapt to different scenarios. If I trained you on how to drive, you can drive anywhere in the world. We want it to be autonomous. We don't want to keep ourselves in the loop with it, just like what's happening with LLMs today. And we want it to have this continual learning capability. So I guess everyone in AI kind of agrees on these things altogether. So, but we're starting from a long way, but we're starting from a very good point, which is today's large language models. So basically these kind of GPT kind of models that we have. And the start of the possibly, I would say, the new revolution that happened in large language models was through the introduction of cognitive capabilities like reasoning. So back, I think in 2023, O3 was released, O1 was released before O3, which kind of showed something new in terms of these AI models that we have. So what we were able to do over there during that time, we were able to put down a lot of compute at the output rather than relying on our own methods that we used to do earlier, which just plug in more data, plug in more training, and then you're going to get a better model to get a better answer, for example. We started using more compute to get a better answer, and that resulted in something that's called the test-time scaling law. So the fact that you think more at your output, you can get a better answer. And then after that, something else followed, which is the planning capability. So this is where GPT-5 is now. And this is kind of what people call as the agentic AI era. So what is planning itself? It's the capability of breaking down a complex task into a sequence of actions in order to achieve a goal, which is something that's very well known in AI. So now talking about these things, so this is basically the current state of AI that we have roughly. It's currently the state of AI that we have with all these autonomous agents that we have now over um, uh, in our world, where you just give that autonomous agent a high level intent. It knows what to do. It knows how to reason, to plan, to take actions. But that's really good, but just for language. So basically, the current forms of reasoning and planning are good enough for these language models, but they're not enough for the real world agents like those vehicles or robots or the wireless networks that we have. That is simply because the world is governed by laws, and which work apart from language. So language works in a way, the world works in a different way. It works in laws like the laws of physics that we have and that we acknowledge that they exist in the world. So, but we are actually on a good path here with this cognitive path. So if we were to continue this path, we would ask the question is that, well, there needs to be something missing around here so that we can actually reach these things because it seems we're on the right path. So we could possibly ask, what is the missing cognitive capability needed to move forward in the world? It needs to be something that is very tied to the world and is exclusive to the world, and which allows it to continue this path of success, I would say. So if you were to dig deep here, we would see that this is something called common sense. So as the name implies, it's it's common knowledge for all of us human beings, that tells us how the world works. It kind of captures our ability of how to make sense of the world and how we understand the world and how we can able to use this amount of knowledge in the world so that we can leverage it whenever we're kind of stuck in the world. So if we do acknowledge that this is what we're kind of missing, and this is the basic trait that we're kind of missing in the world, we can possibly ask, how can we actually bring this common sense into the world? So to bring this common sense into the world, we have to find the component in our cognitive system that is trying to compensate for that. And that is nothing but a world model. So what is a world model? A world model is a model of the physical world that allows humans to understand it in terms of its real-time state, in terms of the elements that exist in the world, in terms of the causal structures, the causality that exists between the different elements of this world, and in terms of its evolution into the future, given that I have this knowledge. So, but we also have to see that the introduction of a world model drives in other cognitive capabilities like perception. Because how would I ever know the future states of my world if I don't know how to capture my world at the current state that I am in? So that would definitely require perception. So at this moment over here, what I can do is that I can zoom out a little bit and probably ask this question, which is, what are we trying to say with all these cognitive capabilities? Remember the path that I was kind of drawing, which is the fact that we have today's AI, we added the reasoning, then we added on top of it the planning, then the common sense through this world model, now the perception. So what are we trying to say with all these cognitive capabilities? We are indirectly acknowledging the fact that we need a cognitive solution that includes all these cognitive capabilities on top of today's AI. And that is something not that far away from the logic that we have or the knowledge that we have, because we already know that these kind of systems that we have today that are mostly built around neural networks, they build on what we call system one in psychology. These architectures mostly refer to what we call as system one, but we have a lot of these missing system two architectures that we really don't know a lot about. And here, this is something that Daniel Kahneman, who is a Nobel Prize winner, uh, he, uh, he kind of verified, or he kind of put down, which is the fact that we mostly rely on the system one, which is our fast, unconscious, associative, automatic pilot kind of way of doing things. But we also have this other rational thinking type of mode, which allows us to take actions, but which is very slow or logical and takes a lot of efforts from us. So if we were to see now how this entire system would look like, if we were to compensate for this system two architecture, how would it actually look like? So we put this down back in 2023. We drew it down back as a new architecture through wireless networks. This architecture was inspired from, by that time, what Jan LeCun, who was one of the fathers of AI, of deep learning, basically, an architecture he put down during that time. What we try to do is that we try to take this architecture and try to fit it over the network and try to see how we can help in this process in driving this new system two capabilities and new levels of intelligence over the network to benefit the network itself and to benefit the agents that are now connected over this network. So, and here I'll highlight here one of the previous talks on the TNB group. I think it was back in either November or December. This is one of our colleagues who kind of called us out here. He mentioned us and he kind of gave us very nice comments. Actually, he called us as stellar researchers during that time that are working at the forefront of 6G communications. And he was kind of posing this work at the forefront of wireless communications and AI, and how we're intersecting with Jan with this vision and trying to see how we can fix things at the forefront. And of course, this is us, Omri. This is yours truly. And of course, as I said, this is based on Jan's vision. And during that presentation, he kind of wished that he kind of wished that we had mentioned Carl, or we have talked about Carl's active inference principle and the free energy principle during that work. But we have to handle each giant at a time. So that was, I think, but during that time, around November, I think we have already contacted Carl, and we already started looking at the free energy principle and how we can actually reach a convergence with the intersections that kind of connect us all together, rather than looking at the discrepancies that differentiate between us. So, of course, the connection over here will be around world models. So, rather than seeing that everyone is working on a different kind of thing, as we're going to see today, basically the three of us, basically even more, I think the current generation of AI even, all of us are trying to solve the same problem, but probably from a different lens. So, so to move forward here, I'm going to give you a glimpse just of how we are going to build this architecture, how we design this architecture, basically. Uh, this architecture looks something like this. So you have the sensing observation that you capture from the world. This is the main interface with our intelligence that we capture. So we sense the world. So in wireless networks, we've already been studying sensing the world over the years. So it's something that happened probably at least over the last 20 years. We had different flavors of that. So we have these, what we call as Internet of Things sensors, for example. This moved on to things like in 6G that we're anticipating, which are called integrated sensing and communication. So basically, what we can do is that we can capture these models of the world. We can sense the whole world through these distributed infrastructure towers that we have, that if you walk around, you would see each 10, 30, 40, 1 kilometer, you would see a base station next to you from which you get your signal. We can actually look at these towers as sensing towers. So we can look at them as very big sensors that sense the whole world through a distributed infrastructure. So as if it's one person that's seeing the whole world all at once, which is something I think just wireless networks are only capable of doing at the moment. And of course, this allows you to build a real-time model of your world. And we already started looking at that back in 2022, I think. So this is one of our previous published work. I don't want to bother you with the wireless details that are inside, but what I want to highlight here is just the fact that we can divide the world onto these base stations that we have. And of course, we have a lot of computing power over there connected to these base stations, and we can use it for a lot of the computations that we need for intelligence. At the same time, I want to highlight the technology, the other technology other than just the world model, which is what we call as digital twin. So the digital twin, you can think of it as a model of your agent. So in the same way where you have in the real world, in the physical world, you have a model of the agent, it has a counter in the digital world, which is basically your world model. You have also a counter of the model of the agent itself, which is called the digital twin. Now that digital twin allows the physical agent to do a lot of things. We're gonna show it in the next slide. So what happens here is that digital twins, once they intersect with this world model, it allows you to predict the future state from your current state at time t. And we know that digital twins are going to be basically a pillar of 6G networks. And that was actually our main goal from which we started working on all the way back in 2022. or 2021. We put down this vision. It was back in, this was published back in 2024 in this paper. But what we wanted to do is to define the operation of this digital twin. So the fact that you are going into the future, predicting at your T+1, T+2, T+N what's happening, which is basically resembles a little bit the reasoning process. Now we're going to see it afterwards, but just this is just to put you in the big picture. And you have this connection here, which is this proactive configuration of the physical twin, which is basically your physical agent in the world. So we're kind of sending a feedback back to the physical world from here. But apparently, in 6G, we still don't know how this technology works. We know that it's going to exist, but we don't know how it works. And it's our role to kind of define this technology. So as I was saying here, so what a digital twin does is that it takes real-time updates from the world, from the physical agent that's in the world, and it returns back some real-time optimization in the world. And what it does is that it does some what-if analysis, counterfactual predictions, some monitoring, and also another work that we kind of tried to prove early on back in 2021, 2022 also, which is to show that these digital twins need to have continual learning capabilities, which is something also that everyone is kind of AI is trying to search for. So now I'll go back to the architecture that I was trying to talk about and look at it in this way. So if I look at it now from a neuroscience and AI point of view, more than just a wireless systems point of view, I can see now that I have this world model. I have this digital twin that kind of intersects with this world model inside. I have other things that compose the world around me, which we kind of call here as assets. And I have this going forward into the future that I was talking about, which kind of resembles reasoning. This is how I actually do reasoning. And if I do this reasoning and I do have a agent that is connected to the network, can I allow the agent to reason about its actions through the world model that I have in order to generalize? So basically, we know that we have these agents that are failing in the world. We do know through large language models, for example, is that if you reason, you will be able to get a better answer. So can we similarly allow the agent to reason, to take a better action in unforeseen situations that it has never seen before, to take a better action in those places and possibly generalize? And of course, for that to work, this reasoning should go back to the policy that exists on this physical agent in the world in order to do this test-time scaling, or what is known now as test-time scaling, where you scale that policy. So you can see here these missing connections that we're talking about. This is what defines a digital twin in 6G networks. And if you are in AI or in the active inference community, you can know that this intersects a lot. You can see this closed loop here, which we're going to build on for our work. So this is the work that I'm going to be presenting today. Of course, the main target is to look at active inference, and try to see how we can pose it as a test time scaling law for these physical AI agents. And of course, we're considering that these agents here are being trained, that they have a lot of intersection with reinforcement learning, for example, and try to see how we can, if we can generalize what we are seeing today in large language models, and to ask the question if maybe large language models are just a special case of the system that we have over here. So, but before we start with the test time scaling and all this stuff, we have to go back to the basics, right? We have to first understand what the problem is actually from the beginning. We're saying that we have these agents that need to reason and need to take a better action, for example. So how does the story start? It starts from somewhere like this. So reinforcement learning has been here for probably for 50, 60, 70 years in AI. What we know is that if we take an autonomous agent like a vehicle, for example, and we train it in the world, we train and train and train until it reaches this point of convergence, after which we take the agent and just plug it in the world, right? This is what usually happens. And at that case, what we do is that we just hope that it just works and that it doesn't fail. But apparently it does fail, and we've showed this through evidently through the examples that I've shown earlier. So what happens is that when the world changes at test time, those agents fail. So we have to first understand what is happening here at this convergence and what is happening at that test time so that it is failing. So we have to go here now to the intersection with neuroscience, because basically if we talk about reinforcement learning, it already has this biological flavor. And of course, active inference also has this biological flavor. So let's start to translate things back to the brain, what was actually happening. So what is actually happening over here, we first have to acknowledge that we're dealing with two parts here. So the first part is the basal ganglia, where your policy exists, and the other part is your prefrontal cortex, which is where the smart part of the brain comes in with all the learning, reasoning, world modeling, perception. So everything happens over there. So when we're doing the training, uh, what happens is that at the convergence, we take this policy, we plug it in the basal ganglia, and we turn off that smart part of the brain. We turn off that prefrontal cortex. And then what happens is that we just rely on our basal ganglia during that time. We just rely on our policy. And this is what we have today. So, but now I'll probably ask you a question, which is, how many times do you think about driving while driving? I've asked this question to a lot of people before. Uh, the answer till now has been mostly people don't think about driving while driving. You're thinking about everything else. You're thinking about your your meeting in the next couple of hours. You're thinking about what should you get for breakfast. You're thinking about drinking your coffee, listening to the radio, everything except thinking about driving. And this is basically true because this is what, again, Daniel Kahneman was saying. So basically, your actions that you take are mostly based on your system one intuition. But he also said that there's this system two here that gets involved in action. So there's this 5% roughly here. So when does this 5% now come into play? This comes into play in situations like, for example, here, when you have a pedestrian that is jaywalking in front of you. Imagine you're driving to your campus in the morning, to your work, and suddenly a person decides to jaywalk in front of you. You have a traffic light that's lighting green in front of you. You're pretty much used to that. Every day you commute over that road, and suddenly the person wants to jaywalk in front of you. And this results in surprise. You feel surprised. So the fact that you got surprised means that you were predicting something and something else happened in front of you. So it's kind of a prediction error in front of you. So, and what would you do in that case? Imagine now with me what would happen. You would start to think. You start to say, oh, well, if I move now, or basically before that, before we start to think, you suddenly you feel like you woke up. Your system two kicks in, that prefrontal cortex comes in back again and takes over. And you start to think now. You start to think in the form of, if I move faster, after asking what happened, of course, and what is happening in the world in front of me. If I ask now, if I move faster, would I hit the person? I don't like that to happen. But if I move a little bit slower in that case, I would probably, the person behind me would also bump into me. So probably I should move my lane, for example. You start to ask all these questions, which are basically the thinking that you would do in that case. And then you would possibly settle on a action like, I should possibly reduce my speed to allow the pedestrian to pass, possibly enough to allow the person behind me not to bump into me. And then I would continue my path. So this whole process over here, I can summarize it something like this. So what we have is that we're taking the state of the world. So if now I have no prediction error, which is the state that I was in just before when I was driving, before I saw the jaywalking pedestrian, I was just going through my basal ganglia and using my policy. But in case I had a prediction error, I'm kicking in back my prefrontal cortex to induce this reasoning, invoke this reasoning again, in order to see what I can do in that specific case. Now I'll ask you another question, which is, where have we seen this system before? And I'm pretty sure all of you have seen this system before. Probably this system, you've seen it in large language models and specifically in GPT-5. So in GPT-5, there was this introduction of a router. that everyone was trying to question. Why is this router in GPT-5? And we're somehow reasoning sometimes we're not reasoning. And in case if we have a tough, hard query, you might sometimes go and say, oh, I need to use a lot of tokens here, a lot of thinking tokens to produce a better answer. And sometimes when you're asking something that is very simple, your typical LLM will just respond to you without reasoning. So we can see now how things are kind of trying to converge with the current generation of AI. So you can see that it has a lot of resemblance over here. So this shows that somehow we're on the right track over here. But of course, in our case, because we have this prediction error, as I said, I have to ask the question, what's happening over here? So this what's happening over here is when I saw the pedestrian is basically trying to do a perception again, try to understand my world again. And from that, I'm trying to think, which includes my counterfactual reasoning or my planning of the world. And after that, just like GPT-5, which gives you a better answer by scaling, your scaling at test time, I also need to have some scaling here at my test time, which is somehow still missing, and we still don't know where that is. So now you see here everything I explained over here. This is just active inference. This is basically just active inference. It's the fact that you are detecting your prediction error and trying to remove it. This is what active inference is, of course. But now, if I go back to the examples that I was talking about in the beginning, I can look at active inference and say that active inference is a first principle that describes how all living systems survive in the world. So, in other words, I can also say that the absence of this first principle in the agents that I have in the world is actually the reason why all those systems are are theoretically dying in the world, are possibly they are not surviving systems in the world. So if this is a first principle of how I survive, how can I imagine that these agents that are supposed to mimic me are going to survive? Which makes it obvious that active inference has a solution over here. So this is basically, of course, this is Carr's work over here. This is astonishing work of how we are able to detect this prediction error, of course, and try to omit it as we live our life. But of course here, and of course this prediction error is due to the conflict between my internal predictions of the world that I am expecting based off my own experiences and what I'm receiving in terms of sensory information. So of course, Carr's work shows that reasoning to reduce surprise is the minimum amount of reasoning in any living system to survive. So, but Carl here, I think his main focus was to look at the survival itself. What we came into play here, and I have to thank here Adil Razi, who introduced us to this framework basically back in 2024, and kind of notified us for this intersection. What we kind of tried to look at here is try to see what happened before and after. So basically, what we're trying to say is that if we look at the system and try to say, before I actually got into the surprising mode, what was my mode? How was I working? How was I operating before that? And the case that I got in this surprising mode that kicked in my prefrontal cortex again, and I saw this, what is the meaning of this? It means that it's an unforeseen scenario to me. It's something that's outside of the typical scenarios that I know, that I have been trained on, that kind of constitute my daily activities, and try to look at it at the other point of view, which is from the scaling point, and to say that if I can scale my actions at that point, would I be able to generalize at that specific moment or not? So in other words, now if I want to connect it all together and try to see it possibly in terms of RL, I can possibly look at it in this way. So what we were trying to do with reinforcement learning is that we were trying to revisit states again and again and again and again and again until we get used to these states. And that's where our policy becomes adequate enough for these states. And as long as we're living in those states, it's actually perfect for us. Our policy is always optimal in that case. And after we reach that convergence, everything is fine. Now, the thing is that those systems kind of worked when the world was stationary. So in places where you have something like chess, for example, where of course you need to do some explanatory moves and try to understand all your world, but it's basically a closed world scenario. When you go into the real world, what happens in that case is that you are suddenly faced with an unforeseen scenario that kicks you outside of those states. So that's something you cannot control. But what we can control, which is through our reasoning, is that if we were to control ourselves or control our world, just like the active inference tells us, we can actually scale back to that policy. And this is actually what we need to do, because I can show you now back with that convergence from a pure physics point of view, the fact that at that convergence, you were actually reaching a non-equilibrium steady state, which is of course based on Carl's derivations, which are basically more than awesome for me. They're astonishing, actually. So at that specific point, when you reach that convergence of your RL system, you're reaching a non-equilibrium steady state. And for order for that system to survive, it needs to preserve that policy and that world model that it has over there. Now, in order to allow myself to survive over there, what we used to do in basic RL systems is that we assume stationary conditions in the world. And that was enough to allow the system to survive, because I would never get to a state where my world is violated, because the rules are static over there, they're never going to be changed. But that's not how the world works. That assumption fails miserably in the world. And then when that assumption fails in the world, I have to go and equip my agent with the first principle that ensures its survival in the world, which is, of course, active inference. So, and of course, this goes even further with talking about Hamilton's principle of least action, which is the fact that you have to not rely on your reasoning all the time, because the first thing you would think about here is that, why do I want to go back to my policy? You can look at it from different point of views. From a physics point of view, you have to go back to preserve your non-equilibrium steady state. From a biological point of view, you have to go back to those states which keep you alive, which I think it's called the homeostasis, I think. And the fact that you need to rely on your policy most of your time. So this is one of the things that people that are now looking in the planning and reasoning point of view kind of try to omit. But physics proves to us that you need to rely on your policy over here. So, and there's something very astonishing over here. If you look at it now, you can possibly see that every living system shows a general objective to survive, and it's an internal objective. So you can look at it now as those vehicle, for example. So you have to drive, so you have to survive while driving. And for robot, you have to survive while walking. So you always have this general objective, which is to survive, which is very well known through theories which are called like the evolution theories. You have to survive, and this is kind of your main goal in life, but you can also accommodate this narrow task with it. So for the first time here, I'm talking about the general and narrow tasks. So you have a general task, which is to survive in the world, and you also have a narrow task for you to achieve that other objective, which is, for example, to drive or to walk or to do any other task that we have in the world. And we can see here that at that point where that system is dying, I would say, in the world, or not surviving in the world, or it's basically it's losing control of its kind of general reward at that moment over there, and that's why it's causing it to die. Of course, that has even it can be discussed from a statistical point of view, statistics point of view, which is it's losing control of its Markov blanket, and that's why it's kind of dissipating in the world. We're gonna add this after to move forward. But for now, I'm going to give just an example of how the system kind of evolves now, if we take this into consideration. So what happens here is that, for example, you're driving normal, you have your vehicle, you have a pedestrian, everything is fine. So you have no prediction error at that specific moment. And this is basically your passive inference mode here. It's not your active inference. You don't need to do any you don't need to use your action in that case over here. And then what happens is that the pedestrian starts to move at that specific case. So he starts to jaywalk, this pedestrian. Once that happens, you start to detect a surprise. In that case, we shift towards active inference. So we switch from passive to active inference over the network. Of course, here I do not want to bother you with the notion of the network here. You can consider the network and the agent to be one entity where, for example, your reasoning and your prefrontal cortex over the network is connected to your policy, which is in your basal ganglia that is on the agent itself. But for simplicity, you can consider them to be one entity. There's a wireless link that exists between the two. So of course here, what's going to happen in the surprise mode, the network is going to engage in reasoning to minimize its surprise through this digital twin that we were attaining of the network and through the swirl model. So what happens over here is that, as I said, because this intersects a lot with the RL literature. So what we're kind of doing over here is that we want to build a value function of the survival that we have over here. So we want to build a kind of a value function over here. And what we're going to do is that we're going to send this feedback, which I said that it has not been discovered back in 6G networks. We're going to send this feedback back to this agent over here so that I am able to scale my policy at that specific moment with the configurations that I got from the network. So for example, at that specific case, the action would be, for example, to decrease velocity to avoid an accident with the pedestrian, for example. And what's going to happen after that is that the pedestrian is going to pass in front of me. I'm able to maintain my survival. And then basically, slowly, gradually, my surprise will be minimized so that I go back to resolving this situation and I am able to go back to my passive inference mode that I was in before I saw this state. So you can actually look at life now, if you want, through the lens of you are passing through different states. These states some are foreseen and some are unforeseen for you. And life is basically just a combination of these. So it's sometimes foreseen, unforeseen, you resolve them, you go to foreseen, and that's how you survive through your life, achieving your objectives, which can be narrow and your general objective, which is to survive. So now we're going to start with the technical part of it a little bit. So as I said, we have this agent in the world. It has a policy, we call it pi node over here. What's going to happen is that we have a twin of this agent, which we call digital. It's a digital twin. It intersects with that world model. What's going to happen is that we're going to do a sensing of our world. We're going to take in all these sensory observations. So, of course, we're considering here that perception is a top-down process from predicted states to sensory observations to try to figure out what the best possible explanation for these sensory observations is. And in case I have a surprise, I will close in this loop and start to think and start to do planning on top of the state that I have here, the state of the world that I have over here. And I start to engage in counterfactual reasoning where I start to think about the different alternative policies that I can have in that specific case. And after I do that kind of thinking to minimize my surprise, what I'm going to do is that I'm going to send these configurations back to the agent itself to scale the policy, of course. So first of all, we're going to elucidate each of these cognitive capabilities that we have here. So we're going to start with perception itself. Of course, perception is, to do that, we first have to define a world model, what we have here. So it's the combination of the observation states and policy that we have. And what we're considering here at that specific moment, at that specific time, t, is that we're predicting our observations. Of course, that needs a prior and a likelihood of what are the observations that we're going to get and the observations that we're getting, and we're going to measure the surprise between them. So, of course, surprise can be captured as a Bayesian surprise process. And we're going to measure the surprise. For each time instant, we're measuring the surprise that we're getting in the world. Whenever that surprise crosses a certain threshold, which is here defined as epsilon, we're going to consider that this is something unforeseen for me. This is something I wasn't used to or violates my world model at that specific case. So there's something wrong in that case. So what's going to happen is that first thing is that I have to figure out my posterior, right? Because my prediction of the world, I lost it right now. I have to figure out what is the true situation of the world that I'm in. And for that, we're going to do the inference basically and capture what is the state of my world at that specific time before I engage in the thinking process or the planning process that I have. So what I want to do is that I want to leverage this model of the agent that I have and the model of the world that I have and engaging in this what if analysis. So this is the basic role of a digital twin over the network. So the model of the world itself is just the amount of information that you have. In active inference literature, the different actions, those that results in different policies, these are actually different copies of you as an agent that drive those different parallel world models, if you want to say. So what I'm going to do in that case is that I'm going to start to think of the different alternative policies. This is what I said when in the example where I said that I possibly, if I move forward, I'm going to hit the person, but if I possibly go a little bit slower, the person behind me is going to bump to me. So all this thinking by itself, what I'm trying to do is that I'm trying to assess the different alternative policies in my brain. And of course, here, what we're trying to do is that we're trying to see which policy measures the best in terms of surprise. Of course, if we measure the surprise resulting from each policy, that would result in nothing but our entropy, because that's basically what we can control. The average of surprise is basically entropy. So, but what we want to do with those calculations that we kind of did in our head is that we want to build this value function I was talking about. So I want to see which action actually minimizes my free energy, or basically before the free energy, minimizes my surprise in that situation. And what I'm going to do after I build this, so of course, relying on what I thought about now, I can use it with some delta function to figure out what the action is at that specific case and try to build a kind of probability distribution. So of course, surprise is upper bounded by, we know that surprise is upper bounded by free energy, and free energy can be modeled as a Boltzmann distribution. So long story short, if I do all of this mathematical modeling, I can send back the feedback to the agent that I have in the real world now to actually do the scaling of my policy in that situation. And of course, before I reach this point, I have to acknowledge something that we also researched about, which is the fact that in situations where you do have surprise, we saw that in studies that what happens is that there's the basal ganglia. What happens is that there's a rush of dopamine that comes at that specific moment. I think it's called from a part of the brain that's called either the SNA or the VNA. I'm not sure about that. Please excuse my limited neuroscience knowledge. But what happens in that case is that you kind of suppress your habitual policy. And what happens is that that prefrontal cortex kicks in again. The prefrontal cortex starts to do all this reasoning, and then it sends back signals down, top-down signals. I think they were called through corticostriatal pathways down to the basal ganglia and shifts the policy in that case. So just to acknowledge that this has biological interpretation at that specific moment. So now to reach the point where we want to reach the scale. So now if we look at it, we modeled perception as inference, of course. We modeled planning as inference. We still have action also as inference. But here's the main point, the main difference over here, which is the fact that that inference now happened. If you really think of it, that inference happened in my brain. That's different from perception. In perception, when I want to do inference, it's actually the evidence happened in the real world. So it's hard evidence. And this is what's known in Bayesian statistics. So it's known as hard Bayesian updates. So what we usually do in Bayesian terms is that we use a hard inference. But since what happened in my brain, it happened in my world model. So this never happened in the world. So this is here, but luckily there's Judea Pearl, who is one of the fathers of causal inference. He actually modeled this process, but in terms of Bayesian nets. So there's a known method here that's called Pearl's method of virtual evidence, where we can actually do is something called soft Bayesian inference or soft Bayesian update, where we don't have to go all the way to actually acknowledge the fact that these evidence that we thought about in our brain happened in the world. So that's why it's softly modulated through this theta parameter that I see over here. So that theta parameter is something called a normalized surprise. So what happens in that case is that if I write it down as a Bayesian inference process, I can write it down in a very nice format at the end. We can see that it's composed of two components, the pi prime that I have, the scale policy that I have. It's composed of a feed forward and an inference term. Now, given the fact that I have this theta over here, which is basically my normalized surprise, I know basically from reinforcement learning is that, and from what I explained a little bit earlier, is that when the world is mostly predictable, I have no prediction error. And that's why I was going through my basal ganglia and taking actions through that way. And at that specific moment, I can see here if my theta is equal to 0, that exponential term that corresponds to inference is basically eliminated. So that reduces my action back to my feed-forward policy, which is something that I know, and it works now in practice. But if we want to look at it from a different point of view now, and this is where the things become interesting, is that when that theta is actually when the prediction of my world is violated, that means that I have a surprise, and that theta is now no longer 0, which means that my policy naturally scales with inference at test time. So I can say it from a different point of view, which is the fact that what naturally scales is basically the policies and not the generative models that we see today. So generative models will scale now because policies scale. And this is something that appeared over here. So the fact that in today's solutions, we made reinforcement learning stationary from the first place. It's not that reinforcement learning was wrong, it's that we did not compensate for that theory of dopamine that comes at test time. So the fact is that we studied dopamine and how it works in the training domain. And then, for example, in my TD error, when my dopamine sets, when I have my error goes to 0 and I master my world, I did not compensate for the theory of dopamine that comes at test time in that case. So basically what we have today in terms of solutions is just a special case of this specific solution over here. And of course, now, since we put this frame now all together, so we can see that, of course, this is challenging to be solved. We know this very well from the free energy principle. It's computationally intractable. So in order to solve the solution, we're going to resort to variational inference, of course, which is we're going to go to the free energy, basically, kind of work. So this is the solution roadmap that we have over here. Of course, we're going to introduce the variation of free energy to perceive the current state after I went into this unforeseen scenario that I have never seen before. I want to understand what happened since I have a violation of my world model. I'll introduce the variation of free energy as an upper bound to estimate the surprise. And then we're going to resort to the predicted surprise in the future, which we want to use in order to minimize the expected free energy. And from there, we're going to infer this policy, this in my brain that I was thinking about. And then we're going to resort to the, from a physicist's point of view, to look at the Markov blanket and see how we can reach this scale policy and model it as a gradient descent. Of course, given the fact that I was talking about an architecture over here from the beginning. So it makes sense to have a gradient descent. And of course, at the end of the road now, what I want, which is to quote Alan Turing, is to say that I want a machine that learns from experience. So this has been one of the quests in AI. I want to have a machine that figures out things by itself in the world and learns from that experience by itself and knows wants to update itself and knows how to learn what it needs to learn in the world. And this is exactly what we can do here with this new experience that we kind of figured out, we generalized to in the world and try to accommodate it into our model. So to start first here, of course, what we're going to do is that we're going to introduce a variation distribution to estimate our true posterior. Of course, to do that, we have to introduce the variation free energy to do variation inference. And of course, once we minimize the variation of free energy, that will result in a minimization of my the KL divergence. I would reach that state, that true state of the world, the Q that I'm searching for. And that would give me a very good upper bound on my surprise at that specific moment. So it's a two-in-one solution. I'm estimating my surprise, and I'm able to do perception and understand the current state of my world, my Q of S again. So of course we have to write it down as a partially observable Markov decision process, a POMDP, and this is its factor graph over here. So what we want to focus on is this S of T over here. So I want to find what is that specific state over here. Of course, using there's nothing new here in the math. It's just figuring out what we need to do. Of course, this we can write it down. It's going to be shown that it's nothing but a variation message passing scheme. So we're going to pass these different messages in order to figure out what our Q of S is. And I have to say something over here, which kind of differs a little bit from what we know in terms of active inference, which is the fact that since we went into a convergence mode once we trained and went into convergence mode, what happened is that I am preserving that pi node in my prefrontal cortex. So here, when I want to calculate my free energy, I'm not actually calculating my free energy over all the different, of course, I'm talking about the variation free energy here, the variation free energy over all my different policies, because I already converged to a certain policy. So I'm going to use that same policy in order to figure out what my free energy is. This is a big distinction here from what happens in the active inference literature. Of course, because you can see here, I'm using my pi node over here, of course. And then after that, of course, I'm going to do some normalization. And of course, this is a gradient descent process. So what's going to happen is that I will minimize my free energy until I reach it so that it becomes a good upper bound on my surprise. And from there, I can calculate what my free energy is, of course, through mathematical operation over here, through this equation. So after I figure out where I am standing now in terms of that state, what's going to happen is that I want to think now at the other part of the factor graph, which is my future states over here. So what I'm going to do is that I'm going to introduce the expected free energy, which is composed of two terms, of course, which is the risk and the ambiguities of my predictions over all the possible alternative policies I was thinking about. So I use just my pi node for the perception part of the story, but for my thinking, I have to look at the different alternative policies that I have, starting from that state that I figured out through perception and through my pi node over there. So of course, here the main differentiating factor is that those preferences, as I said, the fact that I'm visiting those states again and again and again through the reinforcement, I am acknowledging the fact that I can live in those states, and those states actually minimize my free energy. So we can see here that now when we were actually doing reinforcement learning, in the background, we were actually minimizing free energy. But we didn't pay a lot of attention to it because we were surviving in all of those cases, so that we didn't look at that part from the beginning. Because again, we were mostly dealing with closed world scenarios. So after I do that, I'm going to build this distribution of the different policies that I have, of course, based on my expected free energy. And I'm going to use it to build this inference policy based on the actions that I want to look at. So now I have this inference policy, which is nothing but this exponential term that appeared in that test-time scaling law, in that theorem that I showed a little bit earlier. Now, what I want to do is that I want to reach this pi node prime, the scaled version. But of course, this is an intractable inference process. I can't do that. I know that I have my pi node. I know that I have this exponential term, which is also modulated by a theta. So I want to figure out a way of how I can reach that theta in that process. To do that, we have to look at it now from a physics point of view, which is to say that an AI agent that generalizes in the world is a random dynamic system that exists over time. And that survival is one of the main facets of an agent that generalizes in the world. So how we do that in terms of physics, this is through our Markov blanket. So we keep this separation between ourself and the world at every instant in time. So of course, we know that our Markov blanket is composed of our sensory states, active states, the external states, and the internal states. And we have these cognitive capabilities that are happening over here in terms of perception, planning, and action. So, and thanks to Carl's derivations over here, we can look at it from a specific point of view, which is if we were to preserve this Markov blanket over time, we can theoretically show that our states will have to move towards minimizing variation free, basically maximizing evidence, which is the same as minimizing surprise or minimizing free energy. What does that mean? That means that at that specific moment when I was starting, when I had that policy that I had, that my pi node, I have to move towards the action, towards the active states that minimize my variation-free energy. Because if I look at it now as an energy landscape over the Lagrangian that I have over here, the solution that actually minimizes my free energy over here is nothing but the psi that I showed you in the previous slide. That's the inferred policy that I thought about in my brain. This is actually the solution of the minimization of, or the solution that optimally minimizes my variation-free energy. And now I exist at that pi node. And now what needs to happen is that I have to move over that energy landscape so that I minimize the energy and go towards that minima over there that exists at psi. But again here, remember when I said that this is modulated by theta. So what's going to happen is that I'm not going to go the whole way around. I'm going to just move as much as I need so that I preserve myself in that way. And that's going to be modulated by the theta that I have over here. And this is what's going to result in my pi prime over here, pi node prime over here. And of course, this can be modeled as a gradient descent, and we can introduce a stopping criterion to stop the gradient descent at that specific process. And that would result in the policy that would allow me to generalize at that specific state. So that's the policy basically that allows you to move forward when the pedestrian is crossing the road, but not at a pace that would possibly cause an incident with that pedestrian, but also move at a state to allow you to keep moving towards your narrow objective that you have. Because if you think of it here, the best possible action might be to possibly turn off your car and just sit in your place. You don't do that in that place specifically. You continue in a way that preserves that Markov blanket of you so that you always remain separated from your world and that you do not die, and also to continue your goal, to reach your narrow goal. So now, in a nutshell, what happened is that I saw this unforeseen scenario, I generalized to it, I continued now my life is continuing, but now I have a new experience. So as I said, referring back to Alan Turing, what we want is to learn from experience. We want to learn from this experience that we saw over here. And so what we're going to do is that we'll try to update the world model and try to update the variation-free energy and try to insert back the A and B, the transition model, of course, and the observation model, which are not in the active interest literature. So what we're going to do is that we're going to introduce them back and try to find the posterior of these A and B and possibly even the policy pi node that exists over here through inference, of course. So long story short, if I were to find this posterior, we can see that if we model it as a Dirichlet distribution, of course, over my with my prior and my likelihood that I got over here, we can see that we're going to reach this form at the end here, which is basically as a function of my concentration parameters, which are now updated with this experience that I got now. So what does that mean? That means something like this. That means that I am trying to enforce or reinforce that this observation with that state, I want to enforce that connection between them. Now, the same thing applies to my transition model. So, or basically before I go to my transition model, what basically this means is that I'm trying to say that at that specific moment, that state gives me that observations. And if I go to my transition model, I do the same math again, it will result in the same Dirichlet distribution with my updated concentration parameters. And that means I'm also trying to enforce that connection between my transition between those states, my S of t minus 1 and my S of t over here that I got here. So now I'm able to enforce the fact that I might see a pedestrian at that specific point. That connection becomes more powerful, more stronger, I think, at that specific moment, for better terms. And of course, I still have that policy in the world model that exists over there. In the I'm talking here about the prefrontal cortex area, of course. So in the prefrontal cortex, what's going to happen is that also my policy is going to get updated. And if I write down the math, I'm also going to see that it's a Dirichlet distribution with that accumulated new concentration parameters over here. And what that means in terms of the policy is that I am reinforcing that state with that action again. So what I am saying basically is that that action that I took in that specific state where I have a jaywalking pedestrian in front of me, I want to use that action again because it allowed me to survive. Again, we don't know anything about that state because it's unforeseen to us. So I'm going to reinforce that because it gave me a positive experience at that specific moment. And this is here, if I want to talk a little bit probably in terms of wireless terms. So this is another facet of a digital twin that we discovered in this work, which is the fact if you acknowledge that I have a digital twin of an agent and give it this reasoning ability, it does not just allow it to generalize to the unforeseen scenarios that it does not know in the world. It also allows you to introduce continual learning capabilities to the agent, which I talked about earlier in the beginning, which was one of our quests. So now what I have is that I can move this policy that was updated in my prefrontal cortex. It's also going to be reflected back to my basal ganglia. And of course, what we said in terms theoretically, the basal ganglia now exists at the level of the agent itself. So now my model updated by itself. I figured out, I generalized, I modeled, I updated my model, and now I can move forward in through my life, basically. So for our simulation, I'm going to show here a little bit of the simulations that we have. So what we did is that we modeled this jaywalking pedestrian example. So what we did is that we can see, so we used a benchmark, which is a Q-learning benchmark. And of course, in comparison to our scale policy test-time scaling approach, what we can see here is that we never allowed the agent to see that jaywalking example before. We trained it on situations where everything was fine, there was no jaywalking. And then at test time, we introduced this jaywalking example. What happens at that specific time is that the vehicle crashed. So if you can see here, I'm going to use my pointer if it works. Yeah. What you can see here is that at that specific point, so our pedestrian was introduced at this yellow dashed line over here. What happened at that step is that it crashed because it was used to the fact that at that specific moment, when I see a green light in front of me, for example, I would just accelerate. And you can see it here. This is where the acceleration happened at the last step. So rather than it stopping or slowing down, allowing the pedestrian to move, what happened is that it used its own previous historical experiences at that specific moment as if it's blind and just continued moving because it was so confident of itself and it did not have this notion of uncertainty that there's something wrong at that specific moment. Yeah, okay. So what happened in our solution is that at that specific case, the vehicle stopped. It did not, it tried to decrease. So it tried to decrease its speed. It tried to slow down. You can see here that at that specific moment, it slowed down. You can see, I don't know if it's showing in the background, but you have this yellow background over here, which shows that at this moment, the policy scaled. The policy did not just go through just the basal ganglia route. It also moved through with reasoning. So what happened, you can see that the vehicle was taking actions, which is to slow down and maintain its speed until the pedestrian was out of the way. So it went back to accelerating again, and you can see how the policy switched back. So it went back to its habitual case again, and it starts accelerating again so that it reaches its destination, which is at the end of the road. So if I want to look now at the level of the rewards that I have, of course, both the narrow task and the general task are both working on the dopamine level itself. So they do have the intersection, they intersect together with the same reward. So what we're seeing over here is that at that point where my Q-learning solution, my Q-learning benchmark, what happened at that specific case is that when it saw the pedestrian, it moved forward, it crashed, it resulted in a big negative penalty, of course. So at that specific case, what happened in our case is that we were able to detect the surprise at that specific moment. So you can see here we have the rewards that are on top. We had those rewards. What happened since I detected the surprise, the policy scaled. I sacrificed a little bit my reward over here. I'm not sure if it appears, but my reward got a little bit decreased at that specific moment. But I'm still getting reward. That's the difference. Over there, it doesn't result in a big penalty. I'm still getting that reward for remaining alive. And you can see here at the end, what's going to happen is that once it reaches destination, that reward increased. So this goes back to the case of reinforcement learning, which is its premise, which is to ensure that you maximize your long-term reward. Basically, what's happening in the Q-learning solution is that it did not fulfill the premise of reinforcement learning, which is maximize the long-term reward. It sacrificed it for instantaneous reward that kind of got it killed, I would say, at that specific moment, theoretically, of course, rather than sustaining its long-term rewards at that specific moment. And of course, our solution was able to do that because it was able to detect the unforeseen scenario, that surprising scenario of the jaywalking pedestrian at the first place, and adapt and scale the policy in order to avoid the crashing with the pedestrian, unlike the Q-learning solution. And if I want to do a performance comparison now, I'll do a performance comparison between Q-learning, Bayesian RL, and our proposed method. So we want to introduce here, what we try to do is that we try to have two benchmarks. The first benchmark is a model-free solution. The other benchmark is a model-based solution, and try to see how our solution is able to balance between model-free and model-based solution in terms of reinforcement learning. So what you can see here is that we trained the three solutions, the Q-learning, Bayesian, and scale solution. You can see that mostly they resulted in the same reward. And then at test time, what we did is that we introduced this jaywalking example. What happened is that, of course, Q-learning failed, Bayesian RL failed. We were able to succeed, but of course, with less reward. So of course, you can see how Q-learning and Bayesian RL have a very bad reward here. It's minus 21. In our case, it resulted in a decrease in the reward different from what happened in the training scenario. But of course, that was at the expense of the success, as I said. So you can see here that the success is barely unmeasurable in the Q-learning and Bayesian RL case, which is very well known because we have this distribution shift. Unlike our solution here, which shows you that in every scenario that we introduced it in with this jaywalking scenario, it resulted in success all the time because it does not go recklessly and go recklessly just behind its narrow rewards. So what happened is that scaling at that specific moment can sacrifice the reward in order to ensure the success. So you can look at rewards now as cumulative on top of each other. It's kind of like you have an iceberg, if I want to model it. So it's kind of like an iceberg that the big part of it is under the water and the tip is above the water. You can look at it in this way. So everything that is below that water is basically your general survival kind of reward, which keeps you up. And that thing on top, which is just your narrow reward, you can a little bit sacrifice it in order to stay alive. And of course, this happened with just 63% in terms of using our inference. So we introduced also the inference itself. We don't need to rely on it on our time, because we can resort to our habitual policy in that case, is where we don't really need to use a cortex and to model and to look at the models of the world that we have, at least in this specific case that we're talking about. So it provides a trade-off between model-based and model-free models. So, and this is where the learning part comes into play. So the learning part over here, you can see that what we did is that we got this jaywalking scenario. We allowed the agent to see this jaywalking scenario for 50 times. So every time I'm showing it the same scenario, I'm letting it generalize to it. Every time I'm letting it generalize, what's happening in that case is that my surprise is starting to decrease because I'm anticipating that there might be a pedestrian that is crossing, even if the traffic light is green in front of me. So now I get used to it. It starts to get familiar to me. It starts to go from being an unforeseen scenario to something that I got familiarized myself to it. And of course, that means that the belief for that specific case over here is that I predict that there's a pedestrian whenever there is a green light for me, that's going to increase uh, with the experience that I'm going to see. And of course, in terms of the policy, this means that that action with that state at that specific moment, that specific action that I'm taking and that keeping me successful in that case, the belief of it is going to increase with time. So what's happening in that case is that the policy is reinforcing that action with every encounter that we have. And we can see here something very nice, which is the fact that the decision, as of course, as my surprise decreases below a certain threshold, my epsilon threshold that I was talking about earlier, that specific scenario and that specific action become familiar, and now I can deal with it through my updated policy, through my basal ganglia. So what happens is that decision making moves from inference, which is deliberative and takes a lot of force and a lot of energy and a lot of effort, to feed forward, which is very easy for me over time by reinforcing those actions. And this is, of course, this is the continual learning solution I was talking about earlier. So this gives you the notion of transfer learning and continual learning without touching anything. The agent knows by itself when it needs to transfer its knowledge and when it needs to continually learn from the experiences that it's seeing in the world. And before I conclude over here, I probably just now summarize everything that we did in this work. So what we did was we showed that through active inference, we have this natural detector that allows us to detect unforeseen scenarios that can happen in the world, these unforeseen scenarios that we're not used to. It allows you to give you the minimum amount of reasoning that you need to have in order to exist in the world on top of the policies that you have. And with that, you are able to establish a test time, the minimum, I would say, test time scaling law for you to exist and generalize in your world. And that, of course, is the minimum amount of generalization that you need to have in order to exist in your world. And that, of course, in comparison head to head with large language models, I think it's very much clear now, you can see the resemblance of what's happening. So in large language models, what was happening is that we are building the system bottom up. What we're doing over here is that we're building the system top down directly from first principles. And that's why we saw this intersection now between both systems. And of course, now here at the end, I'm just showing that there's a big future ahead for both wireless networks and AI as they move forward. And this is one of the big visions that we're working on, which is called AGI native networks, artificial general intelligence native network. And I think we showed somewhere here now at least what general intelligence can come up with here and over the network, and that these are the pillars that we should build on as we move forward to build more intelligent systems in the future, whether it's world models or digital twins or this test time scaling law that can also be expanded. I assume it can be expanded, at least I hope so. And through building these cognitive architectures to the future. And with that, I'll conclude and I'll be happy to answer any questions. I hope it was lengthy and informative enough for me. Thank you.
Thank you, Omar. Let's all unpause, unmute and give Omar a round of applause for his excellent and demanding tour de force. That was certainly a test time.
I just realized that it's been around an hour and a half.
Yeah, it's been a test time challenge for our inferences. Thank you,
Thank you.
Omar.
Thank you.
Okay, so now we open the Q&A from the audience, and I see Ian Culver already having a question. By all means, Ian, take it from here.
So in this architecture, you have some agents. Let's assume that one of them is a car, and the car has its own world model and it has its own sensors. And then you have this wireless network infrastructure that has a digital twin of the car. So the car is running its own simulation internally, and then the network has its simulation of the car. And then, okay, there's surprise detected from the car's end, and then it will send a request to the network. So then the network will send an update to assume direct control over the planning of the car. I'm assuming that this leads to more efficient usage of compute, the way that you're designing it. Is this a correct understanding of how you intend this infrastructure to work?
Yes, yes. First of all, I think there's just one small clarification, which is the world model exists on the network level. It's not on the agent level. So on the agent level, it's just your model, your pie, basically, your policy. Your world model just exists over the network. And of course, here we're trying to leverage the point that we're coming from a wireless communication 6G point of view, which is we're trying to leverage the sensing capabilities that we have of the world. So of course, the agent itself has the sensing capabilities. Those sensing capabilities it can use for its policy, but the surprise detection itself is through the network. And of course, it relates back to what you were saying in terms of computing efficiency. So I don't need to put down the all the burden of the computing that I may not actually use, because if I were to go back to Daniel Kahneman's figure over there. So basically, we acknowledge the fact that we use 95% of our time, we use our system one. So 95% of our time, we use our policy. So for that 5%, which is, of course, not a lot. It's very important, but it's not a lot. We can sacrifice and put it on the network level. And whenever I need it, I can go on the network level, get that information or get that knowledge and come back to make it more communication efficient, of course, and computing efficient. Does that answer your question?
So my question is to clarify, say that there's a network disruption, and you're saying that the agent has no world model at all on board. So then if there was a signal jam, let's say, then the agent would just stop.
That's different type of that's a very valid point of view over here. I do acknowledge that, but that's a kind of different problem, I would say. So we want to say how much is the system resilient to jamming, and since this is very critical, it's a very critical signal, how much would we be able to uh, to sacrifice the fact that we're sending the signal over a network that might not be that much reliable. I think that's a valid concern, that's a valid question, but I think that goes out of the scope of what we were trying to do here. What we were trying to do was trying to figure out basically how we can connect the system all together, try to intersect with what Jan was saying, with what Carl actually proved with his active inference principle, and what we're proposing, and try to figure things out. Of course, there's always things that you can solve. I don't know, probably like in the future, if we can basically build more efficient world models, we won't possibly even need a wireless network in that case. We can use it possibly for different things, for other things in that case, for other
So
functions.
the system one architecture does not have a world model, even if it's simpler than the network world model.
No, no, at that specific moment, no. No.
Okay.
Yeah. But of
Thank
course,
you.
we can, it can be built, it can be designed. But of course, this is just the, I wouldn't say it's step one. I think it's also step zero. Try to figure things out. Then, of course, we can carry this further.
Okay, because
All right.
when I think of world model, I think of something like Google Maps, where you have maybe a larger precision at the network level, but you can always download a copy.
Yeah, yeah. That's actually that's a very good point, because we're trying to work on that point. But we're trying to work on it from a different point of view. We're trying to work on it from a level of hierarchical world models. And I see how we can do this trade-off between the kind of precision that you were talking about, actually.
Okay.
But that's a very good point here, actually.
Okay. Thank you, Ian. Thank you, Omar. Any other questions from the audience? While people collect their thoughts, I'll attempt the question. So when you introduced theorem 1 on slide 18, I think, just a few slides there. So just by looking at the theorem per se, it seems like there are 3 algebraic rearrangements where the second equality just re-expresses the soft base and update, and then you collapse the exponent in the third. And then you say just a bit more. I think you just go a bit more on the slide, like just a few, there you say that RL is clearly a special case of these equations. But my question to you on this point is this: so Mach-centered reinforcement learning and soft-Q learning already give policies proportional to the exponential of Q over tau that you have there. So isn't your theorem just structurally identical to the soft Q update, which was called, I think, a tilted prior?
So I think at that point, I'm not sure if they use the free energy at that point. So I'm not sure if they look at the free energy point of view. But I think the mathematical form exists. I'm pretty sure it does. The exponential form, it does exist. But what we kind of built here is that we build it through a different point of view. We build it from the fact that if you do consider it as an inference process, and if it's a soft inference process, from a pure biological point of view, which is through imagination, and of course, this imagination didn't happen in the world. If you can build it through that way, it will result in the same form that we already know and we're kind of used to. That's what we're kind of thinking about.
Okay.
It's not to replace it. Yeah.
So then when you say it's a scaling law, it's a scaling law. Do you mean it in the usual sense in which a scaling law is meant like a measured functional relation, typically a power law with a fitting exponent between a controlled variables and a performance metric which you can replicate across domains or regimes?
This is actually one of the angles that we are trying to prove here now, which is something like the power law that you were talking about. We're trying to see if that exists. We're actually talking about it more here from the point of view in comparison to large language models scaling law, which is to say that what empirically appeared in large language models, and it's now called they don't call it as empirical test-time scaling law, but they acknowledge that it exists, but they don't know why it exists. They kind of they stumbled on it and saw that it works. Of course, it was designed, of course, of great engineers. But we're showing that this actually is derived from first principles. So the fact that the free energy principle is based on Hamilton's principle of least action, how it moved forward to active inference, and from the principle itself, you can now build a law. If we acknowledge the fact that every living system on the face of the earth does this, it becomes a law. I think this is the best way to build a law, even.
Yeah, well, there are some people that would disagree with you. The free energy principle receives a lot of criticism for being too general as to being vacuous, but people mostly misunderstand it. If I have to be honest,
that's a beautiful part, I think, in research. I think you always you shouldn't have everyone agree with you. There should be something.
100%. 100%. Thanks, Omar.
Thank you.
Any other questions from the audience? If there are no other questions, let me double check. Then I suspect it's Carl's turn now.
Is it my turn now?
Yes.
High confidence on this one, Carl. Yes.
Excellent. Good. Yeah, that was a tour de force. And yes, so give my best to a deal. How did you come across a deal? He's in Australia and you're in America.
Yeah, so that work that I was I was talking about here earlier. So Adil, as you know, he was actually he's an electrical engineer,
Yes.
and we're basically electrical engineers as well. So we happened to put down this. Where was that paper? It was here somewhere. Is it at the beginning? Yeah, it was here. So this paper over here, um, we happened to write it down in 2023. We posted on Archive. Adil contacted us and told us that this is very relevant to what we were doing, and that he was organizing a workshop back in 2024 with CFAR on world models. And it also
Yeah.
had Jan and other people over there. And I think one of the people over there was actually Thomas Parr. So I got introduced to the fact, and I saw that there's something over there, something that I felt that there's something over there. I did not know anything about active inference. I didn't know any, my advisor by that time knew about the free energy principle and knew about active inference, but I did not have any idea about it. But from what I heard, I saw that this is so intriguing just to hear that there's this big intersection between three different fields. Of course, there's something missing over there. So I started digging deep over there, over there with Adil, of course. And every time we were having like progress update meetings, I was telling him I figured this out, figured this out. We were kind of connecting the dots over all the time. We started with this work. By that time, there was no GPT-5, there was no router, there was no nothing over there. We built the system, and fortunately, that was the last work of my PhD. So by that time, I needed to wrap things up. It was fast enough. And of course, Adil was acknowledging us along the way. We needed to have a neuroscience expert with us.
Yes, because of course he's a CFAR fellow, isn't he? Also, I'm glad you've met Thomas. So yeah, so Thomas has a a very forensic view from the the first principles perspective on these things. Excellent. Well, yeah, I mean, you clearly have done an enormous amount of work and also have demonstrated it working with not only a sort of really interesting scenario, which will, engage all the autonomous drivers, autonomous vehicle companies, but also have done the sort of comparative analyses in relation to Bayesian RL and Q-learning and all that. So, you've done an incredible amount of work, and it is clear that you have got very deep into the weeds in terms of active inference. So what I've done while you were talking is just pick out a few papers that I fondly hope will enable you to continue joining the dots. So I'm not going to tell you anything new. I'm just going to sort of pick out a couple of papers which you may well have already come across, but if you haven't, would provide another nice perspective on the sort of the key moves that you've been making. And just to make sure I've understood correctly, I think the sort of key move you have made is to contextualize the policy, the planning as inference as entailed by minimizing expected free energy, but to contextualize it by conditioning upon recognizing that I'm in an uncertain or surprising context. And that sort of implicit context sensitivity, which I imagine is entailed by rendering theta conditional upon surprise or its variational bound, then that context sensitivity is a thing that is missing from Bayesian RL and reinforcement learning, and clearly is an important advance from the point of view of autonomous vehicle research, in the sense that you are now equipping this agent with not only a sense of uncertainty but also a situational awareness, so which is context sensitive, and that seems to be a really important move, and certainly should be brought into sort of autonomous vehicle research as soon as possible, just for safety reasons, obviously. And it's an intriguing idea that exactly the same Bayesian mechanics can be applied to G6 and networks. And I think you're absolutely right that to regard this remarkable infrastructure that you have with wireless networks as basically an instantiation of a message passing on a generative model is a very sensible and fecund observation. And you can I imagine you can use exactly the same maths to optimize the self-organization of message passing on wireless networks to the edge, to autonomous vehicles, and the like, with exactly the same efficiency motivations, and again appealing to the first principles of least action, as you've alluded to. Just in relation to Ian's interesting observations, from my perspective, having seen these ideas unwrapped in a slightly different context. I'm thinking here of drone research as opposed to autonomous driving cars. The way that I would have answered his question is, well, we're really treating the car as an actuator, and it's got its IMUs and its RGB feed and its LiDAR, but it's just an actuator, and all it needs to do is to know what its IMU should be, given it's a good kind of car. And to be a good kind of car, you need the generative model, and you need the sort of the network and all the federated inference that ensues from that.
I could not said it better. I could have not said it better, honestly.
Yeah, well, if that's true, then I think you can operate the sort of the IMU or the actuator or the car in a very sort of reflexive mode that doesn't have planning as inference on top. If it was sort of denied in some way access to the top-down predictions of its IMU sensors, simply by having it in sort of default safe mode, so it reverts to being a little thermostat or a little and as Ian was intimating, it would just safely shut down and wait for somebody to tell it what to do. That's but that picture, I think, puts a nice perspective on the implicit use of very deep generative models. And I should say I'm using generative models in a way that was being used probably before you went to school by Geoffrey Hinton. So the notion of world models, from my point of view, is a little bit millennial. So a generative model is, is for me, the world model that you're talking about. And of course, they always have a deep structure. So I'm just thinking, you can think about the car as level 1 or level 0, the network as level 2, but within level 0 to level 1, but within the level associated with the network, you've actually got, I think, another level, which is this sort of either level which is running out in time. So now you've got sort of the ability to plan, which you're articulating in terms of a digital twin. So the way that you described it, I would sort of say world model with no ability to model the consequences of your actions in the future, plus a digital twin, which is the ability to model your consequences of your actions in the future, is a generative model. This is a generative model that is equipped now with the ability to model the consequences of your action. And as soon as you've got that, it is now also equipped with the ability to learn the consequences of action, including the preferences. So you now get into the world of preference learning. There's another, I think, something that it might be useful just for you to think about in relation to the last interesting results you were showing, when it's learning now about jaywalking. So it's now not surprised by jaywalking, it just becomes another context. So you could actually think now about having a third level, which is a context. And that context now, you can condition the precision of the habitual policy prior versus that based upon the expected free energy on the context. So now it becomes able to recognize this context and that context and this context, and then reset not just the value functions or the rewards, but reset the theta, so you can condition theta now on some higher level inference, which is effectively recognizing there is there is a particular context. So that would be one thing that you might want to sort of marinate. At the moment, you're sort of driving the theta as something, if I understood properly, something which is the minimal kind of context recognition. So the world comes along in two flavors: a context that I recognize and a context that I don't. And you can just use now the variational free energy to score the fact I don't recognize this context, therefore I must be in a context I don't know, and therefore I need to now change my prior preferences, change everything, the depth of planning, for example, in order to ensure the chances of my maximizing my marginal likelihood or minimizing my free energy. So I guess what I'm saying is that one way of selling this minimal and very fast and frugal approach to the scaling law is that in essence you're effectively building a machine that is context sensitive in the minimal but really fundamental way, in the sense that this is a context I've been trained on, but there are other contexts that I haven't been trained on, and I can recognize that simply by using the variational free energy as a score for being in this context as opposed to another context. And as soon as you discretize or carve contexts into that bipartition, I think then you can fully license a thresholding notion that there has to be a commitment. Oh, I'm now in a context I don't recognize. Because you've discretized it, then you have to you're perfectly licensed to put a threshold on the free energy to sort of operationalize that commitment to this hypothesis or that hypothesis. If one did that, then I'm fairly sure that you probably have already implemented this, but that kind of thresholding is something which in statistics is known as an Occam's razor or an Occam's window. And it's exactly the same kind of thresholding that scientists use when making inferences based upon a nominal threshold in classical inference or a Bayes factor threshold in Bayesian inference. That I am now I'm 99% confident that I'm out of context, learned context. And that would correspond to a variational free energy of about 3, basically, or e to the power of 3, which would be 20. That's log odds ratio of being in this context versus that context of about 20-1, which is sort of the typical threshold people generally use. Anyway, that was me wittering on in response to. Let me, if I can, I'm just now going to enter into a stream of consciousness, and because this is being recorded, although it won't be published immediately, you don't have to remember anything or take notes. You can go for a cup of coffee now. I'm just going to flash through a series of papers which just touch upon some of your key observations and endorse them, and possibly provide a way of extending what you are doing in the future into not into other domains, but certainly sort of join the dots in the way that exactly as you described. So if I'll share, that's good. Now I'm going to have to steal permission from you.
I think you can, Omar, you need to close the presentation for Carl to take it over, or can you steal it, Carl?
Well, when I say steal it, it usually will tell him someone else is requesting.
Carl wants to steal your presentation, Omar.
It was just stuck. I don't know why it was just stuck.
Now what have I done now? Yeah. Oh, I see.
Now you can try to.
Yeah, no, I've got it all sorted. That's brilliant. Right, I'm hoping you can see my screen now.
Yes, we can.
Yeah, I just put this graphic up just because it sort of encapsulates this thinking about the car example operating in 2 modes, where you've got sort of the intelligent mode where you put all your cognitive science into it through active inference, where you've got basically the ability to plan. And if you read planning as or if you read reasoning as the ability to plan, and more specifically, planning as inference in the spirit of active inference, that basically means mathematically that your Bayesian mechanics has action as a random variable because you're making inferences about it. So it's not the actual thing that the car is doing. The actuator is just fulfilling its IMU predictions, but those predictions are generated by some Bayesian beliefs about what it should do next. And that sort of mechanistically, or from the point of view of the maths, that basically means that your posterior beliefs cover not just hidden states of the world, jaywalking or not, but also the action, your beliefs about the action, not the actual control, but the beliefs about the action, which provide the predictions that allow the car to fulfill those predictions so that it can stop or accelerate or decelerate, depending upon the plan or the policy that you have inferred. And this is the most sophisticated structure where, but it doesn't deny the fact that if you just took out the expected free energy by making theta equals to 0, you've still got a fairly functional reflexive kind of mechanics at hand. So that if you are GPS denied or signal denied, then you're just reverting now to a much simpler generative model where there is no ability to plan, and it becomes reflexive in the context that it has learned, and it's learned that it doesn't receive a signal, it just stops safely in some kind of way. But it did strike me, it was a nice way to think about the difference between the maths that you're using, potentially migrated in the G6 context, to understand that as a distinction between sort of merely mere active inference or merely autonomous. So this would work for a thermostat, but a thermostat that can plan and reason in the sense that you mean it is a different kind of thing, but can use, and you're invoking now the expected free energy to do that. One mathematical way of thinking about that is in terms of a sort of a generalized free energy, which I'm sorry, I can't quite work out where we are now. It must be further down here. One way of thinking about that mathematically is in terms of a generalized free energy that has here we are. Yeah, basically, so this is your variational free energy that you've been used to send action, predicted consequences of action that the car can reflexively fulfill. Usually it's sort of IMU kind of predictions. But it's now you put your expected free energy into the generalized free energy, so that now the expected free energy now becomes a prior over what it thinks it's going to do. And then you can generate from that the actual predictions of the sensations of the consequences of it doing that, or the IMU of it actually fulfilling that. But you don't have to. You can just fix this to be something arbitrary, like not moving or doing a little dance. In fact, we do that quite a lot in terms of illustrating the power of this mere active inference in terms of things like handwriting, the stereotype behaviors that are quite safe. You can just replace your expected free energy or planning with this simple, with this system one like prior over this is the kind of thing I do. And it's usually an orbit. It's usually based upon an attractor. Yeah, so this is a very early example from over a decade ago of it using that kind of very sort of dull-minded reinforcement learning like kind of prior to reproduce stereotyped behaviors, which for you, of course, would be safe behaviors, so that the robot doesn't run into the pedestrians. That was a great example. I've never seen that before. Anyway, there are many papers on this generalized free energy. This paper was published in Entropy and it's the sort of most technical paper to date about trying to get different kinds of active inference accounted for and see the relationships between them. And it struck me that, one other answer to Ian's question would have been, well, at the moment we're working on the most sophisticated kind of system, but it could still operate in, even if you remove even if you set theta to 0, that would just entail something. So that was that. But I just want to say, if you haven't done so already, it would be useful, I think, just to socialize or at least expose your work to the active inference community. If you haven't done so already, then a live stream at the Active Inference Institute would be a very good vehicle to do that, just to announce the potential application of these ideas in a G6 context, if you haven't done so already. And the other avenue would be did you attend last year's International Workshop on Active
No,
Inference?
actually, we missed that. We missed
Okay.
that.
Yeah,
But I did watch it online. I did watch it online, though.
Oh, right. Okay.
Watch the recording.
Yeah, I didn't know it was online. They usually make me go in person. I didn't realize it was online. Right. That's interesting to know. Anyway, next year's one is in Spain. I just recommend that because you'll come across lots of people who you'll enjoy talking to, without sort of breaking non-disclosure agreements. The like, people at Honda, are currently very interested in these kinds of simulations. And for obvious reasons, and they come to these meetings. Waymo come to these meetings. So it's just a good place to actually sort of, again, socialize what you're working on, how it could be applied elsewhere, but also meet like-minded people who are thinking about the same kinds of issues in a very different context.
That sounds great, actually.
Yeah, so that's the thing. One little comment. You've used reasoning in a sort of in two senses from my point of view. And again, this is something for you to think about, and the choice of words that you use. So the system 2 versus system 1 kind of thing, which was all the big thing at NeurIPS a couple of years ago, and indeed is the kind of thing that's being now is being tested by things like the ARC3 challenge. I think that kind of distinction can have two interpretations. I'm just putting this out there so you can qualify when you talk about reasoning, how you're using it. In my world, reasoning is beyond planning as inference. I know what you mean by, obviously, if I can plan, and I have a set of counterfactual plans under my digital twin, or I can roll out into the future and explore a discrete number of policies in terms of accruing the path integral of my expected free energy, then that is clearly reasoning, in the vernacular, because I'm thinking about things, and you can start to use words like intentional behavior. So if I got the ability to sort of model myself doing things towards particular outcomes, then those outcomes by definition are intended outcomes because they haven't yet happened. And therefore I now have a calculus of intentional behavior, which I can call reasoning about what I should do next. In my world, that would just be planning, or planning as inference, and is clearly a really important thing. Reasoning in and of itself, in not, I think, quite in the system 1 versus system 2 sense, but reasoning more generally, when we're talking about abstract reasoning, is sometimes cast not in terms of policy selection, but in terms of model selection. So it's actually structure learning or inferring the very structure of the model in and of itself. And sometimes people use reasoning in that setting. So this is another kind of reasoning, which it will be nice if you were aware of and thought about, because you can actually apply the same expected free energy approach, not just to making moves which will maximize the information gain and augment my situational awareness. So, for example, we haven't talked about this yet, but what I will come to is your kind of expected free energy is missing the epistemic part. Therefore, you're missing an opportunity to point your RGB feed at the jaywalker, because you're going to resolve uncertainty about whether the potential jaywalker is walking or not. So that requires, this is the intrinsic motivation you get in robotics. And it's a really important aspect of situational awareness, where it's not, where the action here is not so much accelerating or decelerating the car, it's where you point your camera. There will be certain sort of actions which are a much more information gathering epistemic sort than the pragmatic kind. Do I move forward or not, according to my goal to get across to the other side of the of the zebra crossing, as we call it in England. So that's one example of the expected information gain part of the expected free energy, which would normally be added into your scaled expected utility expressions. If you now apply this expected information gain to the very structure of the model itself, so now if you now took your model that has now learned that there can be jaywalking. So now there are two contexts. This is a zebra crossing that does not contain a jaywalker, and there's a zebra crossing that does contain a jaywalker. Now, if before you've actually learned these two contexts, there is an opportunity now to think about, well, perhaps this car, well, the car policymaker is really quite sophisticated and actually now can entertain a hypothesis that there could be a jaywalker. Now, what would they need to do, and what would the optimal actions or policies be to resolve uncertainty about whether there is another context or not? And that's what artificial reasoning in this spirit would address. It would be operating in a way, designing experiments in a way to resolve uncertainty, not about states of affairs, latent states or hidden states, but the very structure of the state space itself in terms of a hypothesis space. So I just put this up just as a, I put it up early because you were talking about reasoning. I thought you'd be interested in this. This is still under review, but I just found out, I didn't realize this, it's actually on archive.
Yes.
So you can read
I've
all
seen it
about
before.
it. What?
I've seen it before.
Oh, right. I didn't, sorry, my apologies. Oh, well, you've
Yeah,
seen that. That's
because
good.
because no one's
I didn't realize it was up there. And of course, oh yeah. So I just put this up just to sort of reiterate to reprise the conversation with Robert about the functional form of the expected free energy. There's a nice figure here somewhere.
Yes.
Yeah. So, as far as I understand it, what you are focusing on is the expected extrinsic value, because you've got this V here. And furthermore, what you're now doing is scaling this, or applying a certain precision or scaling parameter theta in the spirit of a soft Bayes-Max. In my world, usually things are articulated in terms of precision parameters, which are just scaling of log probabilities that you can put into you can take as an exponent on the inside of the log operator, so that now you've got a sort of more or less precise probability distribution. I just sort of reiterate the point that at some point it would be nice to include the intrinsic value or the expected information gain in your expected free energy. It's not relevant at the moment. It certainly isn't usually relevant in autonomous vehicle or drone research, simply because there's not much ambiguity to resolve, because normally you choose all your sensors to be extremely
that's actually one of the things that I happened to mention, but as a footnote in the paper, that here we're not looking at the So another formulation of this can be to look at it from an information gain point of view, which is the fact that I am in an uncertain situation now where my certainty about the situation that I am in is at threat. I don't know if this is if I'm not sure if this is the situation that I am in, what it is now, and this results in some uncertainty about me, and I need to go try to gain more information about the state. And this explains why we have this information gaining curiosity, I think I would say. It's artificial curiosity to kind of figure out what was happening at that point of view. And it results in, if you may recall, the first question I said at the beginning, like, what was happening at that case? The first thing that you do in that case is to ask a question because you want to resolve the uncertainty behind it. And I think that leads to the point where I resolve the uncertainty, but to make myself more efficient, this translated into a learning at the end of the story. And so
Yes.
learning
Yes.
is kind of a byproduct of correct inference at the moment. So I think there's a loop now between learning and inference together.
Yes, yeah, absolutely. And I mean, what one way this this loop is sometimes discussed is in terms of the depth of planning. So you can, if you like, you can look at, this is not the best graphic. In fact, I will remove that. Where's it come from? Yeah, this is Lance's formulation here. Yeah, but yeah, I just put this up. I'm not going to go through it. I'm just to introduce the notion that when you're talking about evaluating policies, you can think of it in terms of deep tree searches. So this depends upon something which may be practically relevant for your your formulation. So policies can come in two flavors. They can be sort of tied to the an initial time point of the kind that would be useful, say, for economic games that have some, say, time-dependent change in preferences, or some contingencies are going to be encoded in what is usually cast as a hazard function reference to the first point in time. And that means that all your inferences using the variational free energy can now be conditioned upon all the policies I could be pursuing from the beginning of this game or this interaction. That's great for modeling sort of choice behavior in an economic game setting. It's not necessarily apt for autonomous vehicles or real world situations. So you can greatly simplify the problem by saying, no, I can do one of a number of different policies at each and every time step. And I now just need to run out into the future. I don't need to know what happened in the past to infer what policy I'm pursuing. I can just run out into the future. And in just running out into the future, of course, you can now consider policies as different permutations of actions, and then you induce an impossible tree search usually. And that tree search can be truncated if you reach something that's almost impossible because it is so surprising, very much in the spirit that you're using the theta. But you can actually use the expected free energy to abbreviate or truncate the tree search, or a path down that tree search, as soon as you encounter something that's extremely surprising or has an expected surprise. And one limiting case of that, of course, is that everything you do is going to be, apart from one thing, is going to be extremely surprising. So you actually reduce the depth of your planning horizon actually shrinks very, very quickly, so that you're in the flow, as it were. And of course, what that looks like is you're actually putting theta to zero, because the depth of your planning is so trivial, because you've got such precise beliefs that this is obviously the thing to do. So you can get if like an emergent kind of efficiency above and beyond the variation principles of least action, simply by doing the thresholding that you're talking about. Yeah, it is a thresholding based upon not in this instance the variational free energy, but the expected free energy as a function of time. So it's a sort of stopping criteria, not on whether to plan or not, but on the depth of planning, which seems to be distinct from what you are doing, but exactly in the same spirit.
Yes.
You could put your theta now on a tree search into the future, but now it's based upon the expected free energy conditioned upon this policy, and hopefully demonstrate the same kind of efficiency saving in the context of that. This is a sophisticated scheme, which does it's just I just put this up just because I think explicitly talks about the stopping criteria. And I think that's nice because you can sort of talk, you now explain to people like me at least that the principles of least action entail a path integral. A path integral over what? A path into the future. And as soon as I get a massive expected free energy, I know I am now not, I cannot be pursuing the path of least action. So I can just not do that anymore. And if there's only one path that allows me through in terms of the path integral, then I know exactly where I'm going, and I'm going to know pretty quickly when I'm going, and therefore I can use my thresholded theta in this instance of expected free energy, to make me as efficient as possible. So that was just something I thought it would be interesting to see where you could take that.
And I think I just have to highlight the fact here that the fact that our vision was based on Jan's vision from the beginning, we kind of used the reasoning in the same form that he kind of uses, which is through the term that you said. I loved it so much. The search part basically. It's reasoning as search and optimization. So as I said at the beginning in the slide, we're trying to build on the points that connect together, connect us all together to the same point so that we can hopefully reach the end point that we're all targeting at the end.
Right. Yes, I'm smiling because there's Jan has a particular view about uncertainty and the temperature of the free energy, which
I had a long read about that to understand why was that a point of conflict actually. I understood the fact about the temperature, and I think what we did around here with the uncertainty kind of proves that uncertainty can be plugged into the
yeah,
deep.
absolutely, yes. I mean, I'm sure he's changed his mind now, but when I last spoke to him about this, he was all for zero temperature schemes. I should say here, theta is a temperature. It is the thing that sort of, if you like, gates the uncertainty. Very much in the spirit you might imagine an attention head in a transformer architecture would do.
Exactly.
But of course, there's no explicit
Exactly.
uncertainty.
And here, I think one of the kind of distinctions that I want to say, and probably hear your advice about it, is that you can see here that what LLMs are trying to do is that they're trying to pay too much attention, I would say. So it connects back to what the argument that I was saying a bit earlier, which is the fact that it's as if they're trying to build the system bottom up rather than build it top down. So they're trying to
Yes.
pay attention to everything rather than, because they can't compensate for this other factor, which is captured through the system too, basically, or the free energy, or the surprise or prediction errors that come from the other way around. They're trying to focus too much or pay too much attention on every possible detail over there, so that whatever they want to find, they can find inside their structure. They memorize it, and it's in this big kind of I don't want to contrast LLMs to policies, but it's as if like a policy. It's as if like a big policy that contains everything inside it, and it pays attention to everything so that it does not have to compensate for the lack of a prefrontal cortex, or to reasoning, or to um, to this planning that we're talking about. It's as if it's
Yes, no,
yeah.
no, absolutely. Yeah. I mean, when people start conditioning the attention heads on a deeper level, then they'll be getting closer to the kind of thing which I think active inference would subscribe to, and what you are implicitly
and I think that's why it kind of the intersection happened in a very natural way as I said, GPT-5 was not there once we designed the system, but we were kind of saying that we do know that reasoning is a kind of automated process. So what's the most natural way to automate this reasoning while maintaining our efficiency and while also agreeing between the math, the physics, the biology, the neuroscience, cognitive science, whatever people like Helmholtz were doing hundreds years ago. This has to be a specific instant of a bigger instant. And by that time, when it happened and GPT-5 was released, we kind of verified our hypothesis. So we were kind of in the uncertain state. Then we were in a certain state that, oh, well, this is actually the right process. So the argument is that LLMs are actually good, but if we were to look at them in a different point of view, it's that they're good in language, math, coding. It's not a coincidence. It's a design, but we're not able to see the bigger picture because we don't know that they're a kind of a special instant of the bigger system. So once you look at it now at this system, you would say, well, that kind of reasoning, the chain of thoughts that are happening inside, they are true. They are valid because they work with a kind of structured form of reasoning through language and mathematics and those stuff. And that's why they're valid, but they're not the end of the road, I would say.
Yeah, no, well, as you rightly pointed out, once you move away from language, that mechanics just cannot work. Yeah, I have to say, from my perspective, learning to reason is not reasoning.
Exactly. It's mimicking it. Just you can fake it. You can fake it until you make it, I think. Yeah.
Yeah. Well, and as you're intimating, I think that's the distinction between an engineer and a physicist. Yeah, Jan is certainly an engineer, and I'm certainly a physicist. Yeah. So he's one that.
But I can say from my point that I know that he knows about this work and he likes it.
Good. Yeah. Good. Well, you're doing your best to bring people together, aren't you? So that's good. I'll just quickly whip through these. If you haven't read this paper, I think you'll enjoy it because it sort of just covers the neuroscience of policy selection based upon dopamine, which would be one instance of your or one of the variables that you could associate with theta, and how it certainly does fit very much with interactions between the prefrontal cortex and the basal ganglia when you look at the actual update equations and the maths based upon variational expected free energy. So there's a lot of neuroscience that you could certainly appeal to. You talked about substantia nigra, which is there somewhere. So this was a paper done with Thomas, which sort of brings together the variational message passing with the brain. Another thing that you might, if you haven't read already, have you seen this about federated inference?
No, actually, this is new for me.
Okay, so it just may have a few bits in which would again allow you to join the dots in the context of belief sharing with the multiple towers.
Mm-hmm.
So it's decentralized inference, but when when you're talking about common sense, you're emphasizing the common ground that is implicit in common sense. And in active inference, that common ground and common sense entails a partially shared generative model. And as soon as you have a partially shared generative model, you've got the opportunity to pass messages between towers, for example, that enable your posterior beliefs to inform my posterior beliefs because there's a common support to the generative models. And it's the free energy minimizing solution, the path of least action, shows that the right kind of message passing, i.e. communication or belief sharing, is an emergent property of free energy minimization. So I thought you might like that just when you start thinking about federating this. So you've got a smart city that now can actually send commands to one car that actually knows about an accident around the corner, for example. And do it really efficiently just by passing posterior beliefs that are common to, you don't pass all your beliefs, but just the ones that are actually shared. So it's like having multiple eyes, on the streets, as it were. But here, framed in a neurobiological context with about language and communication, but the maths you will recognize as something that could easily be generalized. Just to sort of promote the importance and your focus on theta and gating and scaling, which I repeat is always in my world read as a precision parameter, a softmax parameter, an inverse temperature parameter, coming back to Jan LeCun and his inverse allergy to temperature. If you get into the neurophilosophy literature, it is exactly this contextualization of theta read as a precision of something. It could be the value function, it could be the prior preferences, it could be the trade-off between the expected free energy prior over policies versus your habitual prior over policies. All of these things can be equipped with a precision parameter. It is this conditioning and deep structure which some people believe is necessary for phenomenology, for actual experience and for awareness and the like. Again, I won't go into this, but as you build deeper and deeper hierarchies that are linked purely through conditioning, for example, the theta on some other part of the model, then you get into very deep models that now some people believe have the ability to, or would be necessary for any given artifact to actually experience itself or act upon itself in a metacognitive kind of way. So that I thought you'd be entertained by. Oh, no, that's the same thing. Yes, that's Lars. That's what we've just done. Yeah, anatomy of choice. Hopefully, have you read this literature? It's a decade plus old now, but it is remarkably close to your treatment of theta. But so in this paper, the components of the expected free energy were actually weighted by a gamma parameter, which I think plays a role of your theta. And the derivations of the updates to gamma, which are not simply equated with the variation of free energy, but were changed to minimize the variational free energy by treating the theta as something that had to be inferred as a random variable itself. This gamma is your theta, in effect, and it behaves exactly as I say, very much like dopamine. So again, speaking. So yes, here's a VTASN that you were referring to as a source of the gamma. So this was written really for sort of behavioral economics and choice theory, less about autonomous vehicles. But you might find the maths interesting, and certainly as a point of endorsement of talking about dopamine. I think it is exactly this sort of balance between a priori, what do I engage my habits, or do I now have confidence in my planned beliefs? So this gamma parameter was now effectively your theta parameter. Was this basically a reflection of the precision of my beliefs, my posterior over the policies based upon expected free energy? And if that's like flat and I'm uncertain about anything, then that goes away in relation to I recourse now to the habitual response because I got absolutely no idea what to do. So that I thought that might be interesting if you have.
I think I just have to add one more thing here, which is the fact that although in the example I focused on autonomous driving, it was just a simplistic scenario. I would say it's just to bring your imagination just to the spot, because this is something trivial that all of us face in a common real world scenario. But of course, this scales to any system that needs to interact with the world, whether it's a robot, so it has to move in that way, because if it does not move, it means it is losing control of its Markov blanket, and basically it's just dissipating in the world, and that kind of explains the phenomenons that we're seeing, the uh, the hallucinations, I think, that we're seeing in the world.
Yeah, I accept that fully, but I would still encourage you to use the jaywalking example. I think that really
Yeah,
does
of course.
sort of. I think that's an excellent example to use because it's so practical. It's so you'll
Exactly.
engage people in autonomous vehicles and all sorts of things. You know, that's got all you need at the moment, I think, to tell stories about intentional behaviors, context awareness, context situation awareness, context sensitivity, and everything that you need
And I do
to.
have to, and I just have to do give credit to Jan for the example of the vehicle that is falling off a cliff. It's from his slides. I
Is
inserted the robot on, so it's from him. He uses it as as an argument.
I didn't.
Yeah.
I haven't seen him do that one. Okay, that's interesting.
Yeah.
Um, this is a similar piece of work, not quite as sort of squeaky clean in terms of the physics and deriving variational updates for the precision or the scaling parameters. But I think you might find it interesting from another perspective. This is not dopamine. This is adrenaline. I'm talking
Oh,
about arousal. Um, so you may find this of interest, but done by work by
yes.
Anna Sales, who's now actually the CTO of a drone research company,
Oh,
very much into these
nice.
issues in a very practical way. Um, oh yeah, just to reinforce the important observation, you can learn your preferences. I thought that was an important one. There's not much been written about that other than by some work by Noah Sajid, who's at MIT now. But again, if you don't know this small literature, then you will have friends there that certainly celebrate the importance of being able to learn your own preferences. This is the kind of thing I do. And because I've done it before and I'm still me, this is obviously the right kind of thing to do. So I like that argument. It's
I'm very much enjoying what you're showing me right now, because when we built the system, we built it just by logic. We did not look at if there's literature or somebody looked at the theta and the gating, and if we can learn the preferences or so. We just use the fact that we know that the system exists in the world. It is working. Probably, as you were saying, like from a pure engineering point of view, which is there's a problem that's lying at that last point. What's happening at that last point before the system breaks down? And we were kind of connecting it to all the theories that we know everywhere. And from there, we kind of understood that when we were doing reinforcement learning, for example, we were actually minimizing the free energy in the background. But we didn't actually see that because we were playing around with the world in a very simplistic scenario. So, of course, it had a lot of branches, like the trees that we're talking about for Go or chess or whatever, but it was not at the level of complication that is when you're dealing with the real world. And the fact that we had the physics with the non-equilibrium steady state that you also derived, we were seeing that, well, we were reaching that non-equilibrium steady state for us to survive at that specific moment with the convergence. What is happening at that point? We kind of connected the dots to see that, well, survival, we were ensuring the survival by the fact that the world was not changing. But then once we looked at it from the other point of view, which is you need to have the first principle that ensures survival, once your assumption fails, were kind of at a point where we're seeing like somebody should have figured this out before. It sounds so intuitive that we were trying to search that we were able to see that each block by itself exists. So, but then the big picture, when you connect everything together and connect it with the current state of art that we have today in AI, things become very intuitive for any person to explain and to enjoy it. To actually see that this is what we are seeing, because the evidence is that was the things that we see every day, just like the example of the jaywalking that we're talking about.
yeah. Well, so you should repeat what you've just said to the Active Inference Institute on a live stream. They'd like that. Yeah.
Yeah, but once you understand, that's the trick about it. Once you really understand active inference and the pre-energy principle, because I remember I saw one of your works which talks about that it doesn't become more simplistic more than the pre-energy principle.
Yeah. Keep
So I
everything
believe
as
that. I
simple as
believe in
possible, but no simpler. That's the
yes.
Einstein's missive. Good. That's it. That's all I have to say. Thank you very much.
Thank
I'll
you.
stop
Thank you.
sharing now.
Thank you.
Yeah.
Thank you.
And now
We
what
thank
happens is,
you.
yeah,
Go
Rob's going
ahead,
to make
Carl.
us clap and all that. Yeah.
So I'm making the claps now, Carl. I'm making you clap now.
We're going to make the clapping. That's what's going to happen.
Okay. So I suspect now, with again high confidence, that it's about time to once again congratulate you, Omar, for your excellent presentation. Tour de force, 3 times repeated in this description. So there you go.
Thank
And
you.
also thank Carl for his extensive synthesis as usual.
Thanks to you also, and thanks to Carl for the extensive comments, which I will surely take into consideration. Thank you so much.
Sure.
It's been a
So
pleasure.
I will upload this to YouTube with a private link and then share the link with you so you can consult it whenever you want.
Hopefully just a couple of weeks by the time we get some feedback from Carl and other colleagues, and then we can just reset on. Thank you.
100%. Thank you, Omar. Thank you,
you.
Carl, and see you next time.
Thank you.
Bye, everyone.
Bye-bye.
Thank you.
Bye-bye.